We've all heard about black holes, but I don't think most of us know what it really is. Fundamentally, it is a region in space so extreme that gravity, time, light, and even the fundamental structure of our reality behaves such a way that we cannot really comprehend. Every black hole begins at the end of a massive star. Stars exist in a delicate equilibrium between two opposing forces, gravity that pulls inward and nuclear fusion that pushes outward. For millions to billions of years, this balance sustains their luminous existence. But fusion is a finite process. When nuclear fuel is exhausted, outward pressure falters and gravity does its thing. The stellar core collapses in a fraction of a second, imploding at enormous speed and triggering a supernova explosion that can briefly outshine even an entire galaxy. If the remnant core contains less than about 3 solar masses, neutron degeneracy pressure halts the collapse, producing a neutron star. An object of staggering density where a teaspoon of matter would weigh billions of tons. But if the mass exceeds this limit, nothing known to physics can stop the collapse. Gravity continues compressing matter beyond the neutron stage, beyond any known form of degeneracy pressure, forcing the core inward until, theoretically, its radius shrinks to zero. This means complete loss of spatial extent. All the mass of a star is crushed into a point of zero volume and infinite density, which scientists call a singularity, where space-time curvature becomes infinite and the known laws of physics cease to function. Still, this singularity alone is not the black hole. Surrounding it is a boundary of space-time predicted by Einstein's general theory of relativity and first mathematically described by Carl Schwarzschild. Einstein revolutionized gravity by describing it not as a force but as a curvature of space-time caused by mass and energy. Schwarzschild solved Einstein's equation for a collapsed mass and found that if enough matter is compressed into a sufficiently small region, space-time curves so severely that all possible paths lead inward. This boundary, where the escape becomes impossible, is called the event horizon. The event horizon does not physically exist. It is a mathematical demarcation, outside of which escape velocities are less than the speed of light, and inside of which escape would require exceeding light speed, which nature forbids. Thus, nothing, not matter, not radiation, not information, can escape once it crosses this horizon. To understand this intuitively, consider escape velocity. On Earth, it is about 11 km per second, determined by mass and radius. If we increase mass or decrease size, the escape velocity would get higher. If we compress enough mass into a small enough volume, escape velocity surpasses the speed of light, rendering the object invisible. This is where the term black hole comes from. At the heart of this region lies a singularity, a one-dimensional point containing immense mass where density and curvature diverge to infinity. Physicist Kip Thorne famously described it as the place where the laws of physics break down. This breakdown is not unexpected, because singularities occur where quantum effects should dominate. Yet, general relativity does not incorporate quantum mechanics. A future theory of quantum gravity, perhaps string theory or another framework, may one day replace singularities with something physically describable. But for now, they mark the limits of our knowledge. Some theoretical models even predict naked singularities. Singularities not hidden behind event horizons, though none have been observed yet. And their existence would challenge the predictive power of relativity itself. So far, we have described the idealized form of non-rotating Schwarzschild black hole, but real astrophysical black holes almost certainly rotate because the stars that form them rotate. When such a star collapses, angular momentum is conserved, producing spinning black holes, described by Kerr's solution to the Einstein's equations. Rotation introduces profoundly strange phenomena. A spinning black hole drags space-time around with it in an effect known as space dragging. The region where the dragging dominates is called the ergosphere, a distorted oval-shaped zone outside the event horizon where nothing can remain stationary relative to the distant observer. Objects entering the ergosphere are compelled to co-rotate with the black hole. In 1969, Roger Penrose proposed that rotational energy could be extracted from this region. An object entering the ergosphere could split, with one fragment falling inward and the other escaping with more energy than it originally possessed, effectively stealing rotational energy from the black hole. This Penrose process may explain the colossal relativistic jets observed from quasars and active galactic nuclei. Despite such complexity, black holes are remarkably simple in description. According to the no-hair theorem, they are defined entirely by 3 properties: mass, spin, which is angular momentum, and electric charge. Any other information about the matter that formed them is lost to external observation. In reality, astrophysical black holes are expected to have negligible charge because any net charge would rapidly attract opposite charges and neutralize. In 1974, Stephen Hawking introduced a revolutionary idea that merged quantum mechanics with black hole physics. He proposed that black holes are not completely black but emit radiations due to quantum effects near the event horizon. Quantum theory allows particle-antiparticle pairs to form spontaneously in vacuum fluctuations. Normally they get destroyed instantly, but near an event horizon one particle may fall inward while the other escapes before annihilation. To the distant observer, the escaping particle appears as radiation emitted by the black hole. This is known as the Hawking radiation. Because the escaping particle carries positive energy, the black hole effectively loses mass, leading to gradual evaporation over an immense timescale. A black hole of the equivalent mass of our Sun would require around 10⁻64 years to evaporate, vastly longer than the universe's current age of 13.8 billion years, while supermassive black holes could persist up to 10⁻106 years. Hawking radiation, though widely accepted theoretically, introduces the black hole information paradox. If black holes evaporate completely, what happens to the information contained in the matter that fell in? According to quantum mechanical theories, information cannot be destroyed, yet evaporation seems to erase it, making this one of modern physics' deepest unresolved problems. Approaching a black hole introduces tidal forces so extreme that they produce the vividly named phenomena of spaghettification. Gravity decreases with distance, so the gravitational pull on an astronaut's feet would exceed that on her head, stretching them lengthwise while compressing them sidewise. For a stellar mass black hole, this stretching begins well outside the event horizon and would tear matter apart before crossing. Supermassive black holes, however, possess event horizons so vast that tidal gradients at the boundary are weaker, allowing hypothetical observers to cross intact before destruction deeper within. Observational astronomy has confirmed such tidal disruption events. Stars have been seen shredded as they venture too close to a massive black hole, their debris forming luminous accretion flares detectable across vast distances. Perhaps the most counterintuitive effects involve time itself. General relativity predicts gravitational time dilation. Clocks in stronger gravitational field tick more slowly relative to the distance observer. Imagine an astronaut descending toward a black hole while a companion remains far away. To the distant observer, the astronaut's clock slows and the emitted light becomes increasingly redshifted. Near the event horizon, their motion appears to freeze. The astronaut never seems to cross but instead fades into darkness. From their own perspective, however, time flows normally and they cross the horizon without noticing any boundary. Looking outward, the astronaut would see the universe's future unfolding at accelerated rates. This asymmetry produces a form of one-way time travel. An explorer hovering near the event horizon could experience a short duration while far more time passes in the outside world, effectively traveling into the future. Given that black holes emit no light, their detection relies on indirect evidence. Astronomers search for stars orbiting unseen massive companions, analyze Doppler shift in stellar spectra, and measure X-ray emissions from an accretion disks formed as matter spirals inward and heats to extreme temperatures. Systems such as Cygnus X1 provide compelling stellar mass black hole candidates, even more dramatic than Sagittarius A, the supermassive black hole at the center of the Milky Way, inferred from the rapid orbits of nearby stars around an invisible mass of millions of suns confined within a region smaller than our solar system. Such observations confirm that black holes are not just theoretical curiosities, but they are fundamental cosmic structures, shaping galaxies themselves. In essence, a black hole is not just an object but a region where space-time folds inward so completely that escape becomes impossible, where time dilates, where quantum processes glow faintly at the edge of darkness, and where classical physics reaches its limits. They are laboratories for extreme gravity, testing grounds for theories yet incomplete, and cosmic reminders that the universe is far stranger than everyday experience suggests. At the boundary of every event horizon lies not only the end of a star but the frontier of human understanding, a place where knowledge itself approaches a gravitational limit and beyond which our current physics, like light, cannot escape.